Okay, hello everyone. Thanks for the introduction. Thanks for the organizers. The conference so far has been great. So today we'll be speaking about my current work where I use machine learning for the aim of producing IR spectroscopy. Spectrum. So we heard already through previous presentations the importance about having IR spectrum available. So I will not repeat this information. In particular, in our group, we are interested in the study of polyaromatic hydrocarbons, and in general, are these kind of compounds. And these compounds are relevant in the space science, in nanoscience, and environmental science, and they also have health applications. I think in general people are more familiar with the static way of calculation IR spectra. In my case, I do dynamic calculations, and to calculate the IR spectrum from in a dynamic way, you do molecular dynamics. What the difference in these two families of method is that in this case we have a continuous signal as opposed of the static where you have discrete signals and then you smooth out. And in this case also the method allows to the exploration around the potential energy surface around the minimum structure. Also it offers the advantage of being able to tune the temperature of interest, and allows also for describing the solvent contribution, and it doesn't assume a priori any harmonicity, so intrinsically it's anharmonic. Everything is good, but this is expensive. That's why it's not so widespread. Our main goal then is to reduce in some way the cost of these calculations, and eventually to come with the rule of thumb and let's say a guidance for people who want to do this kind of calculations, see how are they done. So the way it's calculated, in this case you are is different from the static calculation. So you collect the dipole moment all along a trajectory, and then you have all this information in time, and then you apply Fourier transform and you go from the time domain to the frequency domain, finally getting the IR. Important is to know that for this to be valid, you need to work with an ensemble of trajectories. Okay, so in our work there are different schemes, but in our work we are using the MBT, what is called MBT-MBE scheme. And so first we have an equilibration step where the optimized structure is equilibrated in parallel runs, with the aim of having non-correlated structures here. And so we go from one structure to have different structures, and from here, so this part is where our business is where we want to compute the IR. And the particular what is particular about these simulations is that the time steps needs to be super small. I mean, in comparison to the equilibration, and in general, it's about 5 times what smaller than what would usually use for, I don't know, to study reactions. So we are speaking about trajectories of 100,000 steps. And the expensive part that is at each step is the calculation of the forces that is done at our initial level. Of course, this increases the price with the size of the system and the level of theory. So what we do is instead of using forces calculated by ab initio, we use machine learning forces. This is not a new approach. There are many people using these machine learning forces for dynamics. So this is the general scheme, but for ab initio. But if you want to use machine learning, you will have an extra step, meaning you need to train the model. So to create models, we produce the data. We are not taking data from anywhere. We produce it. And I forgot to mention that all the calculations are done on QChem, So far it's not for the public. I implemented now, so hopefully in the future, near future, it will be available for anyone who wants to use it. So the interface with SGDML machine learning model. This is from the group of Kachenko. So what we are doing now, we have QChem, we have geometry and energy. We go to SGDML, we use a model, and then we predict the forces, and in this way we propagate the trajectory. Let's speak a bit about costs. This figure is from the literature. So it is there is an hypothesis called the smoothness hypothesis, and it states that when we go higher in level of theory, something that is more expensive actually goes in favor of a machine learning model. Why? Because the potential energy surface, instead of being all bumpy, becomes something softer, and this is an advantage. It's easier for a machine learning model to learn something at the higher level of theory. And this is actually, well, I didn't put here the paper, but it's shown like in an example where they raise the level of theory, and without touching anything else, the accuracy goes up. Okay, so this is where we are saving, right? Then we are spending. We need to have the training data. So in general, a few things to take in mind: that SGDML is not a deep learning, a huge architecture. So this is a kernel model, so with few thousands of training data points, it should be good to go. On the negative part, we need to say that it's not transferable. Okay, and then if we tune the temperature and we produce the data, we need to work with data that is produced at the temperature of interest or higher. This is not this does not correspond to my case, but this is like a general, like having in mind, like when you increase the temperature, you explore more areas on the potential energy surface. So if you, for example, sample at the higher temperature, you are sure that you are going to explore more places on the temperature that you are interested on. As I said, we are interested in paths. The time is going fast. Today we present results on Fen and Tren. And for comparing the different results, we chose to use the Parson correlation coefficient instead of RMSD or any other measures. This is justified. There is this nice paper where they compare different similarity measures, and they come up with PCC being the most convenient one. So we ran long trajectories. This is ab initio results, and we see that already at 2.5 picoseconds, the positions of the peak will not move anymore. So here, if you are only interested on the positions of the IR spectrum, here you would cut your simulation. But as you let the simulation evolve, you see that the intensities are changing. So you will run until you see that the Parson correlation coefficient gives you a plateau. So you have a converse spectrum both in the positions and in the intensities. We have analyzed different data, and we are still doing analysis on this. So we have, for example, one data set of 100K points. This comes from parallel MBE trajectories of 15 picoseconds. And to have a taste on what are we covering in the potential energy surface, we see that this is tight. This is one electron volt, and the forces 12 electron volts. So from all this data, we are not using this. I said this is a kernel model. We're only using a small amount of data. Here I just list some examples, and we see that at 6,000 points for training, we have an error in the forces of 0.067 in the forces, and 0.21 in the energies. You don't really gain a lot, but I wanted to see what was the best that we could get using 6,000 points. And from 6,000 points is this line, the yellow one. This is, so I said that we use Pearson correlation coefficient. So the accuracy, once you train, you cannot think that this accuracy will stay all the time the same. What we observed is that as the time passes, you are losing a bit of accuracy. In this case, we started from almost 1 and we lost about 0.3 in similarity. But we see that actually this, if we put slope, we see that if we start by model that it has a less accuracy, it tends to degrade faster. I didn't put more because the idea is the same. But so yeah, from going from a spectrum where only the peaks are converged to a fully converged, you lose a bit of accuracy. And okay, so we have two areas in the spectrum. We have the fingerprint where we find the CH binding mode out of the plane for this kind of molecules, and this zone where many things are happening. Aside from the CH stretching, you have overlap of other overtones and combination bands. Making a zoom on the fingerprint, here we get to the final thing that we wanted to see how ab initio and machine learning compare, and this is what we get. I think it's pretty nice. We have some differences. I am not presenting here. I did not quantify this difference so far, but it looks like promising. And okay, so with this I conclude. I am almost on time, and we see that at 2.5, this is something that I saw also for other systems, that around 2.5 picoseconds, you have already the peak positions converged, and you need about 15 picoseconds to have a fully converged spectrum. This is already a repetition, and I hope with this I gave you a taste and convinced you that SGDML is a good alternative to be used to produce IR spectrum in an alternative way. Thank you so much.
Thank you very much. We have time for questions.
Mm-hmm.
So thank you, very nice talk. So my question is, I see that the convergence seems very good, except there's some weirdness in like multiple peaks, but that's aside. How much faster is it to run this machinery? How much less computation time?
Okay, so I think I finally spoke about the smoothness hypothesis, and I didn't say a big point. So depending on the level of theory and the system under analysis, machine learning, this model performs 5 to 10 orders of magnitudes faster than ab initio, and is more expensive than semi-empirical. But here comes the but. So what I am working on is, because this is my first contribution to QChem, and this is so you are working, you are interfacing software. So this is where I need to. So I don't have an answer. This is the short answer. I don't still have a final answer on how faster it will be, because I need to improve this timing.
Okay, thank you.
So thank you for the really nice talk. I have two questions.
Yes.
One, are you machine learning also the dipole moment, or
No. So there are people modeling the dipole moment. Unfortunately, now I don't remember the author. It's a shame. But they are using. So I think people, well, at least people that are in machine learning area, they are familiar with the work of Beller and Parinello. So the same idea that Beller and Parinello use for energies, they do at the same time the dipole. So with some differences, but the idea behind is the same. And so during molecular dynamics, they use Beller-Parinello, and they also predict the dipole. And for you that you also use atomic polar tensors, there are also people modeling atomic polar tensors.
And the second question,
Yes.
on the convergence,
Yes.
do you see a different convergence trend between the different spectral regions in the sense, do you see, for example, fast mode, high frequency mode convergence before or?
I did not, let me think. I mean, I have the data in my mind. No, I didn't really see any, no. No, what I do see is that that when the time goes by, the area of let me see. So this area reduces. It goes down in the intensity, not so much as these things go up. So these modes go up. This is what I see with this kind of systems. Maybe it's not the case for others. But,
Okay, thank you.
Okay, I'm sorry, I think we have to move the further discussion to the coffee break and let the speaker again.